This information is brought to you by Charles Sturt University.
Okay, so thanks for waiting around. So I'm Michael Kemp. I should close the microphone. So I'm a lecturer in mathematics and stats. So I've taught this subject, I don't know, 7 or 8 years ago. So I've taught it once before. I do remember it, that's okay. What I also do is I teach maths to different sorts of people. So I did multivariable calculus last session, etc. So I teach lots of other calculus subjects. I also teach stats. So I really do like maths. My background is I did a Bachelor of Science degree, and I did major in maths. That's why here I am. But I also did a major in computer science as well. I like maths more, so I went more in that direction. But I am familiar with these things, so as well, the computing. So who here is doing a computer science degree? Who's not? Maybe is a bit. What sort of guys are you doing?
Bachelor of General Studies.
General Studies. And
I'm IT.
IT. Okay, so the subject very much is pitched at the computer science. I'm sorry in advance, I guess. Nevertheless, discrete maths is a much more of a general sort of idea, and we'll look at applications beyond that. Because if you are doing computer science, we'd like to know what the applications are beyond it anyhow. So it's really been designed as an equipping tool for computer science, looking at lots of different maths that you might need for it. That's sort of where the subject's pitched. But in doing so, just looking at lots of different mathematics. So that's my details. So I live in Orange, and I work in Orange 3 days a week at this session. So on Mondays and Tuesdays, I'll be down here. I'm in building S15, as I still think of it, or 1292, and level 3. I'm remote. That's my number and my email, and you can contact me at other times as well. So, as I said, Wednesday to Friday I'm in Orange. You can see me on my Orange office if you happen to live that way. So some people sometimes live in Orange and commute down. Okay. So, what I'm going to do is got my lecture slides here. So, what I'll do is, this is the slide version of it. I produce a book format, which is to get rid of all the, doesn't waste so much space. And I'll put those up on the Interact 2 site. So if you go to the Interact 2 site, go to class materials, you'll see the lecture notes that I've got for the first topic, essentially. And that means you don't have to write down everything. So sometimes there'll be blanks in here that I'll fill in during the class. It'd be good idea for you to do the same. But don't forget to do everything. And it's up to you. You don't have to read in advance. I don't require that or anything like that. But up to you how to learn. They're recorded, as you can see behind me here. The microphone's directly above you. You can see the white ones up there. Pick up your voices pretty well as well. So be wary of that. I try to have... It's recording me rather than you at the moment. So we won't have your faces. So if you really don't want if you really don't want to be in video or you can be quiet, I encourage you to talk. It's actually beneficial to the distance students. There's more distance students than internals. And so they really do benefit from these recordings especially. And you guys might as well, if you're sick and you want to catch up, etc., or do revision. It is better normally to come live if you can. But I'll leave it up to you. So, just want to talk about admin stuff to begin with. So the main details of what you're required to do in the subject outline. Just want to pick out just a few things from it more than anything else. That's me. I had most of those information already for you. So I said this subject is just about introducing what's called discrete mathematics. So the mathematics you sort of need for computer science is one way of thinking of it. There's two sorts of mathematics, I guess you want to call it. One is continuous, the other one is discrete. So discrete means there's gaps between it. That's what the word discrete means, just gaps. So we've got just gaps between stuff. That really means integers. That's a common idea, but you can see it in all sorts of things. So for computer science, that might mean graphs, where you've got distinct elements. And where would you ever use that? Well, you want to do when you want to do timetabling. You need to use the graph theory to understand how to do a timetabling algorithm. So continuous, on the other hand, is when you've got lots of decimals instead. And where the mathematics that's designed for continuous stuff is called calculus. Now, we will not do that in this subject, so we'll do no calculus in the subject whatsoever. Having said that, when we go through some of it, you go, oh, that looks vaguely familiar with what I did with it, with some integration or whatever it might be. There are links between the two. So this is not a calculus subject. But nevertheless, despite it not having calculus, it does require a bit of practice with mathematics at the same time. And so I really do assume you're actually familiar enough with algebra, etc. So I think you really should have done a calculus-based subject at school, because that just forces you to get the maths required you need. Or if you haven't done that, at least do Maths 105, just as an extended bridging course, which I think most people have done, looking at transcripts this morning. So I think most people are on that boat. So if you do Maths 105, this is a big step up in difficulty for Maths 105. Just want to make that clear at the beginning. So if you're good at maths, fine. If you're not, that means you'll have to put more work in. And the only way of doing that is to do lots of practice. If you plan that in advance, you can be okay, but just beware of that. Okay. So the things that we're going to look at, so the topics, is look at the basic understanding of discrete maths. So it's looking at sets and logic. Looking at how to do different types of counting. So working how many different things there are. So if you want to try to crack a password, how many different options do you have to try? Can a brute force method is going to work, or that sort of idea. Looking at probability, which you can use for, say, modelling in computer games. So just look at different discrete probabilities. That can be really important for developing software. Graph theory, a really important idea which underpins lots of algorithms that you might see. So as I said, timetable is an example. So working out how to allocate everyone to a timetable really is just about colouring a graph, actually. And so understanding what graphs are and what you can do with them is pretty important, pretty handy stuff. Looking at the idea of what an algorithm is, so functions you might think of. How do you work out if it's a good one or a bad one, and how you evaluate that, something to look at. And a key mathematical idea is looking at the idea of recurrence relations, which is, so if you ever had a differential equation, it's the discrete version of that. So they're pretty important math stuff. But we'll look at them very much in the idea of trying to work out if you've got a good or bad algorithm. And finishing off looking at Boolean algebra, which is logic, again, and just how to implement it in different ways, so logic circuits. So that's sort of the quick overview of the whole subject. So each of those corresponds to a chapter of the study guide. They're not all the same. So each of the first 4 have one assignment next to it, worth 10%. In the final exam, there's 5 questions in the exam. Each of those has 1 question on it. That's how it pretty much works out. So that's sort of the breakdown of the subject. And so if you look at the study guide and various materials, you can see that sort of breakdown there. These are sort of the learning objectives. This is how I set the assessment items. And they really just correspond to these various things. So the first one is just be able to pick out different objects, so graphs, sets, logic, etc. Next one is you have to be able to prove stuff. So that's an important part. We have to really learn how to do that. Next one is about numbers. How can you deal with numbers? So in ITC 161, you might have looked at binary, so we'll look a bit more about that. Next one is about doing the probabilities corresponding to counting. Next one is about graphs and algorithms. And the last one is about the recurrence relationships. So these are all learning objectives, pretty much saying you can do all the stuff in the different topics. That's what it pretty much says. So as we go through, you'll need to make sure you can do all these things. That's what I'm going to assess you on. So it's pretty clear as you'll get to it. Mentioned that one already. So the way at the end of the day is, no matter how good or bad I am as a speaker, or how good the materials are, or etc., at the end of the day, you're going to have to do the practice. That's the only way you're really going to learn it. And so you're going to have to sit down. So we'll do, for internal classes, we'll have tutorial tomorrow. A bit more of that in a second. And so in that time, you'll get a chance to do some exercise yourself. You'll have to do more of that outside of class too. So in the study guide, there are lots of exercises throughout. I recommend you should aim to do all of them by the end of the session. Just do them gradually, it's fine. The textbook has heaps more exercises. So if you find the study guide's not enough, then the textbook could be useful for that. But certainly the study guide, I think, is what you need to do every single exercise in that. So the materials you need, there's the subject outline which details most things what I've said already. There's the topic section which is Interact 2. That contains a few things. The most important of them is the study guide itself, so you can see the link there. So I encourage you to download it, put it on your iPad or laptop, whatever it might be, and you can go through it. You can print it off if you want to, but you guys are probably tech savvy enough, you can use it quite easily on many other different devices. There are other things there too, of lots of extra resources which just enhance what's in the study guide there. So videos from YouTube, etc., all pull into one. So that's pretty handy. There are readings for the various stuff there. There's the other resource is the textbook. So as I was saying before the recording kicked in, you may or may not need this textbook. I mean, I'll leave you to be the judge. The study guide is self-contained. And so some people can do very well in the subject by just going through that and coming to classes. So if you're not coming to classes, if you're a distance student, you can't come to classes because you're in a different state or whatever it might be, having a bit more depth might be really helpful. Sometimes you guys feel you might learn more from this. It has heaps more exercises, and if the study guide's brief, it's only a few hundred pages, but this is a few thousand pages in comparison. Or is it really? There's appendices to the law here. So actually find a real page. So about 1,000 pages in comparison. But the study guide's only about 300 maybe. So, yep.
This isn't really relevant to that, but I was just wondering where we can find the tutorial sign-up.
Okay, I'll tell you more in a second.
Cool.
So the Interact 2 has lots of other stuff too, which has the lecture recordings, online meetings for distance students, etc. If there was a tutorial sign-up, it would be there, but I'm not going to do one. So what I'm going to do is, because there are 24 people in theory in the class, there's only 21 here at the moment, and we'll all have just one tutorial, so just put everyone in one group. So the time for that will be the room which is bigger, so that's the 12 o'clock class tomorrow. It's only for internal students. So that's room 416. Why did I pick that room? It's bigger. The other room's not small, big enough. So everybody will be in the same tutorial.
Oh my god, that's all
We have 6 hours.
That means we've got a 6-hour class block. From 12 until 6.
Oh my god.
Would you like me to try to find a different room at an earlier time slot? Is that what I'm hearing?
Yeah.
That's disgusting.
Otherwise,
It won't happen for tomorrow, unfortunately, but I'll look at it for next week.
A lot of us already got 7 hours of class tomorrow, so.
9 till 6.
You can bring your lunch, it's okay. Makes it better.
Rest in peace.
So it's a 1 hour tutorial, just a 1 hour tutorial. And it will be the 12 to 1 slot, so in room 416.
Okay.
That's applicable for everybody. And the reason is the class is just small enough to be able to squeeze it to one group. So I didn't know if I had to have 1 or 2 groups. Part of the tutorials is you don't have to be quiet in those. I mean, apart from munching and lunch, if the case may be, you are allowed to talk to each other. And again, that's always a useful thing, right? So you can always learn from each other. And so for distance students, I encourage them to try to find other people to meet up with too. And so even if you guys, I mean, who doesn't live in Bathurst who's here? So some of you guys might find it easier to meet with people outside of Bathurst, and maybe some of those distance students live where you live. And so maybe forming a study group with those people would be really helpful. And so I encourage everybody to go to the forums, introduce yourself, just say where you come from, and when you see where people come from, you go, oh, they're really close to me. And in today's world, you could use many other ways to meet up with people as well, of course. So utilise people where you can. And I'm always here to help. That's the plan too. There's the forum. So this is the discussion board. Really important for lots of people. Distance students will probably use it more than internals for the obvious reasons, but everyone's welcome to use it and to respond. I will check it regularly. It's good just to see any really important announcements I will not put through that. I'll put through the main announcement tool, check it via email. But people often put questions up there and I'll answer them. So if you've got a query, I don't know how to do this, it might have been covered there, and you can ask yourself. You'll need a calculator for this subject. I won't bother showing you mine because it looks too old, but that calculator there, if you can hold that one up, would be fine. So a bottom of the line scientific calculator, like this bottom Casio one there, is perfectly acceptable. You will need one for the exam, etc. So if you go down to the co-op and say, can I have a scientific calculator, they'll sell you one quite happily, I'm sure.
Well, they make money, so they're definitely going to sell you one.
Yes. But you can get one from Officeworks as well. If you don't want to give it to the university. It
doesn't even go to the uni, it's co-op.
I know. So there's 3 hours of lectures a week. They are all recorded, as you can see above me. The internals will have 1 hour tutorial. So as I was mentioned, the distance student will have an online meeting, which is something I'll do similar stuff. You are welcome to attend if you wanted to. I'll do it via the online meeting tool. So everyone is welcome to attend, but it's designed primarily for distance students. So don't feel if you're an internal student, don't feel you have to attend. It really is basically to replicate that tutorial experience of distance students. That's one of the intentions for it all. So it gives them a chance to interact with other people and etc. I will get you to do stuff in classes. So make sure you bring your calculator and pen and paper to every class so you can do that work that I want you to do. You learn more that way, that's the intention. Assessment. There are 4 assignments corresponding to the first sort of 4 chapters. The second of them is an online assignment. It's similar. I mean, all those assignments are similar. The online assignment just pretty much means instead of having to handwrite the answers, you type the answers into the web browser instead. That's the main difference. And why did I pick that one? Partly because it's in the mid-session break, so it's easier to hand it in for you guys. And 2, it's the one that's easiest to do that for. I would prefer to do it the last topic, but I couldn't.
Is it timed?
No. So you could go on today, look at the assignment. You can go and look at the assignment today and come back next week and do a few answers. It saves them as soon as you type them in, come back just before the due date and finish the rest of it, so it's not timed. It's just like any other assignment. You really can access it whenever you want to, type it in when you want to. You don't have to do it all in one go. As soon as you hit the submit button, that's it though. So don't hit submit until you're really ready. But otherwise, it's the same as always. So, that's due with the submission break, I think it is. But you're more than welcome to do it earlier, just like anything else. And there's the final exam. The final exam is a must-pass exam, which is common for this faculty. So, so the assignments are really making sure that you are equipped to be able to pass the exam. That's one way of thinking about it. All the assignments are there, so you can access all the assignments right now. If you just go to the Interact 2 site, go to Assess Minds, you can see them all, including the online one if you wanted to. So assignments are really important. You can use software like Maple or Wolfram Alpha to help check your answer if you wanted to. But it has to be your work, and working is really important. So the online one, it's just the answer or not. But for everything else, working, what you write down on a piece of paper, a lot of that proofs, for example, are really important to justify your work. So make sure you do that. In the exam, I'll tell you more about the exam later. This is a simple answer. The main thing I want to tell you at this point in time, although it's technically a closed book exam, so you can't do anything you want to, you're allowed a double-sided A4 piece of paper with anything on it at all. So it's called a cheat sheet, that's the fancy word for it. Or formula sheet's the one I've written down everywhere. You can write everything you want to down on it all. So I'll produce an example one later down in the session. But it's a good idea to prepare it as you're going through. So as you're going through, you're going, I just can't remember this formula. Write it down. So therefore, when you go to your exam, you have it there in front of you. So the reason for that is just so you don't have to remember all the different formulas. Yep.
With our last exam, there was a few things on the back of the exam. Is there going to be stuff like that in this one?
No. So it's up to you to work out what you need to put down.
Okay.
It's about your preparation. Now, I'll give you an example one to show you some of the things that I think would be useful, but I'll do it at the end of the session. So they'll give you an idea of some things I expect you to have learnt, either put it in your head or easy access, one or the other. But it's up to you to work out what you need. So plan that. I mention it now, so you plan it. Okay, so that's the admin part of it. Let's actually do some maths here. And so the first topic is sets, logics, and proof, which I certainly won't do in one lecture. So look at different stuff. So sets are really the building blocks of mathematics. So you can sort of define all maths in terms of sets and functions if you wanted to. You can go overboard with that, and I'll try not to. Certainly people have in the past, but that's the building blocks. So we'll look at that. We'll spend a bit of time on sets, getting that ready, just so we can describe things well. So whether you like it or not, maths is a really fancy, a really useful way of describing many things. Certainly in computer science, and not just that even, for many things in general, it's just a very nice, convenient language. And so sets is just one part of that language. So it's really useful to have that. We'll just do sets today, so just parts of sets. Later on we'll look at logic, which is like true and false values. Then we'll look at proofs, and I'll do proofs as we go through. And proofs is just being able to have a reason argument if something is right or not. It's a simple way of describing it. And that's a really important thing, because sometimes if you're designing a new argument for traffic lights, you need to be able to prove that car accidents won't happen, or like that the lights won't give a phase when both green at the same time, or something like that. So sometimes proofs are important when doing critical algorithms, etc. So that sort of, and even if you don't have to do proofs, that sort of critical thinking is really important. So that's what we'll do is I'll overset. We'll just focus on sets for the moment. So I'm sure you've seen sets before, but let's just go through stuff. So the naive definition of a set is that it's basically a well-defined collection of things, which we'll call elements. What I mean by well-defined is it's clear if something's in or not. That's what I mean by well-defined. So yeah, just give me an element, and I can say yes or no if it's in or not. That's what well-defined is. Otherwise, just a bunch of things. That's the naive definition. So examples are, the bunch of students enrolled in Maths 129 internally, which would be you guys. The numbers that you won a lot of last week, a number of subjects that you've already completed, number of subjects you hope to complete this session, whatever it might be. So just a collection of things. And they can be anything at all. They can even be a set of sets. If you want to go that way, that's okay. That's quite legitimate. So the things can be any things at all. So just some examples of things which aren't sets, to clarify the definition. These are things which aren't sets. The first one's a multi-set. So the multi-set up there has repeated elements. So with sets, every element has to be distinct. So a set, if I can scribble on it. It won't let me write, so I'll do it over here. So in set, if you write a set, set always has distinct elements, so nothing can be repeated. So just be 1, 2 would be the set version of that. So sometimes you might want to consider replicated elements. You can't use sets for that particular purpose. It doesn't mean they're not useful. They certainly are useful, but sets are just the simple one of every single thing. You can have other ideas, which is not a game thing, is a fuzzy set. So a fuzzy set might be, if you want to talk about, say, the collection of bad people. And so let's think of a good person. So what I've got, Jesus, good person, devil, bad person. So that's definitely in or out. So we've just worked out, so I wrote this the other day, so we just worked out who the Prime Minister is going to be, Malcolm Turnbull.
That's bad though. Yeah, Malcolm Turnbull's pretty bad.
Obama.
I'd say devil.
Obama, yeah.
Well, based on the polls, people were a bit undecided about him. He's pretty much somewhere in between, right? So you can talk about it's not quite clear if he's good or bad, somewhere in between.
But the poll doesn't decide whether they're a good person or not. There wasn't a poll of whether he's a good person. It was whether you want him to lead the country.
As a matter of fact, you don't actually get to vote.
A lot of idiots who donkey voted, so...
We don't even get to vote. You only vote your local member anyhow, so... You don't even get to vote the Prime Minister. So there are sometimes when you want to talk about things where it's not really well defined if someone's inside or not. So this is if you're inside the set or not is not well defined. So that's fuzzy. That's useful sometimes, but not really. But not a set. So it isn't clear if someone's in or not. We want to have a very well defined, clear description if someone's yes or no. Yes, in set or no, not in it. Other ones you can have is lists. So 1, 2, 3. Lists have order. Sets don't. So sets have no order to them. So for a computer, it's much easier to put lists in a computer because order's already. Sets are a bit harder because there's no order to them. It's a bit harder to code them up. But so sets have no order. So they have no repetition of elements. It's well defined if it's inside or not, and there's no order to them. So it's just clarifying the definition. Okay, so that's the naive definition. Some guy called Russell managed to break that definition essentially, which you can read the slide later if you wanted to. Essentially, the way to get around his a little problem, if you define a universal set, you define where the elements can come from, gets around lots of those things. So where I said the naive definition said a well-defined collection of distinct objects, you need to talk about what sort of objects they might be. So a well-defined collection of integers or real numbers or something like that. Just if you define the set, you define the universal set where they come from, all okay. If you don't, you can get really weird things happening, which is what Russell's paradox is about. Okay. So I'll skip that though. You can read it if you wanted to. How do you write down sets? Well, essentially at the end of the day, a set's just a collection of objects. You need to communicate it to other people. You need to communicate in a way that they can understand. You can do that in many ways, right? So you've just got to work out who your audience is, which is probably going to be you. If for your assignments, just think of it as being your peer, really. Just someone next to you. Will they be able to understand what you're writing down? So here's some suggested ways of writing it down. You can write down sets as just an English sentence. So the first one go through a bunch of integers from 1 to 10 inclusive. So that's one way of saying it. On the top there, just a bunch of words. It's nice to write down compact notation. So we tend to write down sets using curly braces, and each element is separated by a comma. So as you can see down the bottom there. So one way is just to list them all, which for this one isn't very hard. So the even numbers from 1 to 10, well, there isn't many of them, so you just write them all down. If there was lots of them, you could use an ellipsis, so 3 dots to indicate what the pattern is, and that's all okay. So if people can understand what you're talking about, fine by me. The other one, which is more useful for later ones, is called the set builder notation, where you put a little curly bracket, the type of elements you want, in this case x, and that vertical line. So how I write it? I'll write it down on here. If you open curly braces, the bunch of elements, so we've got a bunch of x's, a big vertical line, and I'll read that vertical line as such that. So this is the open curly brackets is this is a set of x's such that x is an integer and x is even and x is between 1 and 10. So I could bunch all the conditions. And you could combine a few of them together. You could write less words than that if you wanted to. So basically I've got a set of x's such that x is an integer, x is even, and x is between 1 and 10 inclusive. That's called set builder notation. And the key part of set builder notation is have that vertical line. And then one of the things that's really important is you need to say quite clearly what sort of things, what sort of objects these x's are. So here I've got x as an integer. That makes it really clear what type of objects they are. So I'll talk about some special sets that we would normally use, but things like integers, real numbers, fractions are the common ones. But that's sort of so that's the identifying the universal set. That's the fancy way of saying it. makes it unambiguous what it really is. So at the end of the day, you're going to communicate so people can understand it. So just a notation, I'll tend to use lowercase letters for the elements in the set and the capital letters for the sets themselves. Now sometimes we have sets in sets and it gets complicated, so we'll breach that when we get to it, but we'll still get the same thing. If it's a set, we'll try to use a capital letter for it. That's what we'll try to do. So just some notation, we want to say if something's in a set or not. So the way we use that fancy notation is to use this little E symbol to say in. So let's just do an example. So we've got 1, 2, 4, that's our set, A. So the number 1 is in the set. So we say 1 is in A. So that little symbol here means in. So 1 is in A. On the other hand, what about 3? Is 3 in A? No. So we just put it in with a vertical line through it to say not in. Now, if you write the word in rather than that fancy E symbol, I don't care. But you need to be able to read it. So I don't care how you write it back to me, because that makes the same sense to me. But you need to be able to write there. You need to be able to understand when it gets written in a different way. So 1 is in A, but 3 is not in A. So we're building just lots of definitions for the moment, just to get us on the same sort of page. So just as an aside, 2 sets are equal if they have the same elements. So if every element in the first set is in the second one, and vice versa. That's what it means by equals. Doesn't mean they look the same when you write them down. Make that clear. So as an example, here's 2 sets here, S and T. They don't look the same. Can you try to explain to me why they are equal?
Simplify, 2 over 6 is 1/3.
Okay, so 2 over 6, that just can be written as 1/3. Different ways of writing the same number down. Yep.
They've got the same values.
Okay.
It's not in order.
Okay, so the order doesn't matter. So the key thing is, order doesn't matter for sets, so they are the same elements. So it's the same 3 elements in both of them. They're a different order, different ways of writing them down, but they are the same. Sounds good to me. So any justification along those lines is okay. So they are equal. The key thing really is to say everything in S is in T and vice versa. This is so small you can do it pretty ad hoc. For larger sets you have to take a bit more of a careful approach by really testing it both directly. But more on that later. So here's some more notation. Maybe I'll just write them down. So this is an upside down A, and it means for every. So if we have for L, might think about more clear what I'm trying to do here. So if you say this sort of expression, just trying to, so this is backward, so that reads for every x in x. So that means for every little x in capital X. So that's all it really means. The other one we have is a backwards E, and it stands for there is. So there is an X in X, would say there is an x and x which satisfies something or other. So let's just try and make it a bit more concrete. I might want to say that 1, 2, 3, A is contained in B. So 1, 2, 3, 4, 5, 6. So we've got 2 sets. So I just want to talk about set containment. This is my next sort of thing I want to do. So one way of saying that is that for every element in the first set, so for every element, 1, 2, 3, there's only 3 of them, are in the first set, we know that A is in B. It's a very fancy way of saying it, so that every element in A is in B. That's just the one way of saying it. So for every A in A, we know that A is in B. That's just a very fancy way of saying that the capital set A is contained in capital set B. That's all it really says. On the other hand, we know there is a B in B such that B is not in A. That's also true. So we know we can find a number, B in B, so for example number 6. 6 is in B, but it's not in A. Who cares? What does that tell you? It means that the set B is not contained in A. So they're different sets. So therefore we've managed to show that there's an element in one but not the other. That means they can't be equal, for example. And so why this notation is used for is just try to justify some of these things. So here's another thing to try to translate. What does that one mean? It's a joke, if you're wondering. Highbrow joke maybe, but joke nevertheless. So it's set for every upside down A, there is a backwards E. That's how you read it.
So it's not for every. There is.
That's not as funny, I don't think, but anyway.
That's pretty good. That's pretty great. I know I'm debating whether that's funny at all, but...
Okay. We'll move along, I think, might be safest.
Probably smart.
So we want to talk about if an element is inside a set or not. We want to compare 2 sets. So apart from saying they're equal or not, we want to say if one set is contained in another, which is what I mentioned on that slide. So the idea is the subset. So if one set A is contained in another, we call it being a subset of the other one. And you can see that's a fancy way of writing it down. So using the example I've got here, this is 1, 2, 3 and 1, 2, 3, 4, 5, 6, then the first set A is a subset of B, or A is contained in B, but on the other hand, B is not a subset of A. So just put a line through it. So that little U on the side with a line underneath it means subset of. And so B is not contained in A, but A is contained in B. And that's what these 2 lines were saying in a very fancy way. And I give them more just to understand the notation more than anything else. So this is just a way of communicating it. Why I use this stuff, it just makes it so much shorter to write these things down. Now there is a danger. You can make this. You can get rid of English entirely if you wanted to. Just make a bunch of symbols. If you do that, go too far with that, it becomes incomprehensible. So there's a line to draw somewhere of having a bit of abbreviation to make it clearer, but perhaps not too much because then you lose clarity again. So English is important, it really is, because that's the language that everyone will speak here. Okay, so you've got 3 things here. So you've got 3 sets at the top. Is capital X a subset of Y?
Yeah.
Yes.
Okay, so every element in X is in Y? Yep, so definitely a subset. What about the next one?
No.
No.
Why not? Justify it simply.
Because there's a 4 in Y, not in Z.
Okay. Yep. Excellent. What about the last one? Is X contained in Z?
Yes.
Yeah.
But it's also equal.
It's equal as well. And so if sets are equal, they are subsets of each other. So X is a subset of Y. Oh, sorry. X is a subset of Z, and Z is a subset of X. They're both true. And so you can see the notation, that little line underneath it suggests equality is also permissible as well. If you want to get to a situation where you go, I want to get rid of the equals case, I want to have a strict containment but not equals, that's called having a proper subset. So A is a proper subset of B if it's a subset but not equal. And you use the same notation just with that little verb line underneath. So a bit like less than or equal versus less than, the same sort of idea. Despite that looking appealing, we won't use that notation very much. We'll tend just to use the normal subset rather than proper subsets. I mention it just in case we need it really more than anything else. So back to this one here. So X was a subset of Z and Z was a subset of X because they're the same. But X was not a strict subset of Z because they're the same. That's not true. So they're not a proper subset. Okay. So one useful thing, just drawing from that one, is two sets are equal. If you want to prove it, one way of proving two sets are equal is to show that A is a subset of B and B is a subset of A. So just to explain a few things I've written on the board, I've got it as A equals B if and only if. If and only if basically is is logic, which basically says that these two statements are equivalent to each other. So if and only if is another way of saying they are the same thing. So why that's important is sometimes when you want to prove that two sets are equal to each other, the way you have to do it is to have to prove both those individual statements. Have to prove A is a subset of B and B is a subset of A. That's how you actually have to do it in practice. So that's a useful technique, as we'll see later on. Okay. So some special sets. So the first special set is the set which has nothing in it at all, which is called the empty set. So this is a pretty boring collection, but it's good just to have a placeholder for it. So we use the Greek letter phi, as you can see on the slide there, and it's just the empty set, so there's nothing in it. So I just put curly braces with nothing in it at all. Now, by definition, the empty set is a subset of everything else, because all the elements in the empty set, or none of them, are all nothing there, so they always contain everything else, just sort of by default almost. So the empty set by definition is a subset of everything. So people get confused with the empty set, so I'm going to make it going to confuse it even more briefly. What are these some things? What's the relationship between phi and that set there I've written up? So what I mean is, are they equal? Which one is there one a subset of the other, or are they just completely different, nothing related at all? Are they the same? Are they equal? Let's go for that.
One set has an element 0.
Okay, so the first set has no elements, the second one has one element, happens to be the number 0, so they're not the same. So the relationship would be, the first set phi would be a subset of the second one. That's pretty much the relationship, and that's it. Okay? What about the next one?
A proper subset? Proper subset?
Okay, so phi is a proper subset of the other thing. Yep, that is correct. So there, that's our set. So what we've got? So we've got phi is a proper subset of that one. That's true. What else? What other sort of things you might want to say about it? What's the second set? What's this one over here? How would you explain that in words?
It's a set with a set inside it with nothing inside it.
Okay, it's a set containing the empty set. Yeah. Why would you ever think of that? It's the power set. It comes up quite naturally. It's the power set of the empty set. So it comes up really naturally in various cases. Well, trust me on that. So it's not as it doesn't look as silly as it might at first glance. So there is legitimate reasons to consider those sort of things. So we can say that phi is inside the other set. That's also true. In this case, it's unusual to have a set contain another one, but that's fine. And it's a normal subset as well. They're not the same, so it's worthwhile clarifying it. They're not the same thing. So the first one on the left-hand side, that's the empty set. The other one is the set containing the empty set. So it actually contains something, so it can't be empty. Now they look similar at first glance, but they are different. That's the main reason I want to mention it. So the empty set should just be left by itself. What about the last one there? How many elements are in the first set listed? One. How many elements in the second one? Two. So the elements of the empty set and a set containing empty set. So 2 elements, just funny looking ones perhaps. Are they equal? No, because they have different elements, is the easiest way of saying it. Is one contained in the other? Yeah. So the first set is a subset of the second one. And also, as it happens, the first set is an element of the second one. Now, why would you ever dream of those things? You can define all mathematics just on sets. So people have used this sort of notation to define numbers and stuff like that. We will not do that way. It's just easy to use your fingers to talk about numbers. I think that's a good starting point, rather than going from this one. But it's good just to try to wrestle with what some of this notation means to make sure that we're on the same footing. Okay. So I want to talk about the size of a set, and so the word we talk about cardinality, which just really means size. So I'll either use a vertical line, look like the absolute value sign, so the size of the set, just the vertical lines, or I might write an N in brackets to indicate the size of it. So we had 1, 2, 4. What's the size of that set? 3. What's the size of the empty set? 0. What's the size of the set containing the empty set? 1. All okay. For finite sets, it's just a matter of doing some good counting, really. They get harder than that, but you get the basic idea. Any questions before I go? More than happy to interrupt me. I'll let it sink in. People don't. So you can see just here the example. You can see that when there's lots of numbers, I just use the ellipsis, which is those 3 dots in a row. You get the pattern. So what's the size of A, for example? 10. So that means you can understand quite quickly what I mean by that notation, and that's the same thing I expect from you. Just write down something that other people can understand it. We can talk about the cardinality or the size of infinite sets as well. It gets a little harder. So the answer is it's not just infinite. You have to be more precise than that. But we won't. I'll talk about that only really briefly, about the different types of infinite. So just some obvious things really is that if B is contained in A, then the size of B has to be less than or equal to the size of A. And we utilise those things intuitively to be able to check pretty quickly if to get rid of some subsets. Like we used that already. Well, you did already without realising it. You go, well, no, that can't be a subset because there was 4 elements in one, 3 in the other. Can't be a subset. And that was the reasoning. And the same sort of things apply. Just because 2 sets have the same cardinality, it's this one here. So just because the sets have the same size doesn't mean they're the same set, of course. And one could have the element of 1, the other one could have the element of 2. They're both the size 1, but they're not the same set. So that's clear. So cardinality is not the only thing you can use, but it's a way of quickly eliminating some options for you. So we can talk about 2 sets as being equivalent if they have the same size, though. So if 2 sets have the same size, then we call them equivalent. So if A is B, they must be equivalent, but they can be equivalent without being equal. That's possible. You can also extend this idea of equivalent to infinite sets, which is how you really define the size of them. So 2 sets are equivalent in general if you can have a one-to-one function which goes from one set to the other. It's a very fancy way of saying it. And you can define that in infinite sets. So you've got an infinite one infinite set's a bunch of, say, positive integers. Another set is a set of all integers. You can map one to the other and therefore show they have the same size in that sense. And I'll do that later using Hilbert's Grand Hotel to try to explain that. A bit more of give a metaphor around it just to help us understand the maths behind it. So that's the fancier definition. I'll do it. I need a little bit, and the main examples I want to really do about Hilbert's Grand Hotel. Okay. So how we have a break for 5 minutes. It's a good idea to stretch the legs, etc. And then we'll come back. Anyway, enough about coding. So you're looking at some special sets. So these are just ones I want to give special names for. The font I like to use for these special sets is called Blackboard font, and they don't always show up properly in various materials. So I'll do it by hand as well to show you what they look like to handwrite them. So the first one are called the natural numbers, or the cardinal numbers. These is pretty much all integers 0, 1, 2, etc. I would include 0. So they are the non-negative integers. Is a mouthful way of saying it, perhaps.
Michael, what do you think of Pokemon Go?
No comment at the moment.
He plays Pokemon.
He loves it.
Okay.
What level are you?
So the way I write down the set of natural numbers is to put a double line for the vertical one. That's the way I try to indicate. Yeah. So that's what I mean by natural numbers. And it includes 0. That's the key thing. So if I want to explicitly not have 0, for whatever reason, I just put a little plus sign above it to say positive ones. So just a useful set. It's infinite in size. Just the normal. So sometimes we want to talk about these are called natural numbers. So the reason why I call that is the cardinality of any set, of any finite set, has to be in container. That's where it comes from. We want to talk about integers in general. So for integers in general, we use z, and so a double line for the on the z part, and that's 0, plus or minus 1, plus or minus 2, etc. So positive and negative integers. And so we can see that that set of natural numbers is a strict subset, proper subset of the set of integers, for example. They have the same size though, so the cardinality of both of them are the same, but I'll explain that in a second. That's a bit more harder to grasp, definitely. So the fact that it's proper subset, that's hopefully clear. So N for natural, Z, I don't know why that got integers, but it is. So Z for integers. We want to talk about fractions. And so they're called rational numbers. So that's the set called Q. This Q stands for quotient. That's where the name comes from. So a set of quotients. And it's pretty much P on Q, so just a bunch of fractions, such that P and Q, actually, I'll make it as precise as I can, such that P is in Z and Q is in Z, Q not 0. So that's a set built notation. So it's just a bunch of fractions. That's all it really says. And a fraction just means you've got an integer over an integer, and you don't want to. You want to get rid of the divide by 0 case. That's all it's trying to say. So the set of rationals is all fractions. That's what it really is just trying to say. By using that set built notation, and you can see that I've tried to define clearly what the P and the Q are in my set built notation. Can you read? Easy to read? Yeah. So it's a Q, and where you're just doubling up the sides of the, subbing the sides of the Q. So that's how you write in computer font. You have to handwrite it, so it's blackboard font is the fancy way of saying it. So all rationals include all terminating, so if you've got a decimal representation, if it's a terminating decimal, it's a rational. If it's a recurring decimal, it's also rational as well. And you can prove those if you remember your geometric series, etc. If you don't, that's okay. We'll come back to that later. If you don't know what I'm talking about, that's fine. We'll come back to it later. We need it. So rational. So these are just special sets. And so, for example, the number 3 can be thought of as being 3 divided by 1. That's perfectly sensible. And so therefore we can think of as being the natural numbers as being a proper subset of the set of integers, being a proper subset of the rationals. Because any integer really can be thought of as being a fraction, if you wanted to, with that number over 1. Everyone okay with that? What does that bottom line say? Can you translate that into words? Okay, so these are sets. So let's use the word set. I mean, it helps. More than one person said at the same time. So I would say the set of natural numbers is contained in the set of integers, which is contained in the set of rationals. Now, what you said is that, putting it another way, every integer is a rational number. That's what you said, wasn't it? That's equivalently what it's trying to say. And that maps means a bit more. That's good, thank you. Now, want me to try to explain a different way?
Yes.
Can we just go back to the very beginning and just restart?
Okay, so
I might need to light the fire in my head again because it's gone out a couple of minutes ago, actually.
This girl.
what have we done so far? We did these things. What do those two mean? If you tell me that much, you've learned something. In. Next one?
Yep.
Subscript.
Subset.
That'll do. If you can do that so much, you've learned something. That's the key thing I want to revise. Okay. Now, there's been other things, but it's trying to illustrate.
What about the proper subsets and the theory?
I want to keep it simple. That's the key things. So there's a few details in addition to that, but they are the key things. So knowing it's set membership and knowing if one set's contained in another. It's useful to talk about a few key sets. So why am I mentioning N, Z, and Q? Because it's really when you want to talk about, I've got a bunch of things here. What things are they? Well, commonly they're integers. So it's just easy to say, look, I've got a bunch of integers here. These happen to be the integers that are even. All right. So I want to say I've got a set of even integers. how can I write that down in a nice compact fashion? That's really what my question is going to be.
It's just the Z.
And I'm going, well, I've got to have a set. Well, it's a bunch of integers, so it's going to be a bunch of x things, say. In particular, x are in the set of z. So I have a set already, which just is so when I just say x is in z, that's just a very simple way of saying x is an integer. That's all it's saying. Oh, it's just a special font for it to distinguish, because I want to use the letter Z for other things. So this is just saying this is a really special use of the letter. Just notation. So what does that mean?
Pi.
What does that mean?
3.1.
Okay, as soon as I write that down, you automatically think of a particular number, which is right. So when I write down the letter Z, what do you think of? Probably lots of things. If I put a second bar on it, like that, then it really just refers to something very special that way.
Okay.
So it just makes it extra special. That's why I use it that particular way. Yeah, it's putting a double. It's just putting a double line on that one going down. Oh, read it as such that. So it's reading out loud. This is the set of x's such that x is an integer and x is even. How do you write that down? So x equals 2y, well, y is an integer. That's a very fancy way of saying x is even. Now, could you write down x is even? Yes. That's okay. Just want to try to put a bit more out here so you can just try to force you to understand. So this says x, so we've got a set of x's such that x is an integer and x equals 2y where y is an integer. That's how I read that out loud. So I'll say that again. We've got a set of x's such that x is an integer, x equals 2y and y is an integer. That's exactly what it says. So such that, I guess, is the answer to your question.
Is 0 even?
Yep. Okay, so this is a bit of a funny question, but that's a recurring decimal, so 0.99, so 0.9 repeater effectively. You can write that number in a bit more simplified. That's the long way of writing the number. You can write that number down more simply. Do you know what the simplified version of that is? 1. So that's just equal to 1.
In diagonal.
So it's worthwhile remembering that when you're coming down to numbers, there's more than one way of representing them. And so that could be better represented as just the number 1. And so so when we do real numbers in a second, let's do that now actually. So the real numbers, which I write down as the fancy R, so blackboard R, is the set of real numbers. So a real number is pretty much the set of anything which are decimals. So these are all numbers you can do on a number line. I guess is the definition I normally like to use. So pretty much anything you represent by a decimal. Why do they call them real numbers? It's a very fun weird number to use. And the reason is because there are other numbers which we'll call imaginary. And that's the technical definition. That's the technical term for it.
Yeah, I remember my teacher last year.
How about we won't do them in this subject. I can tell you if you want to. Some people already know I can tell. They're not that hard or anything like that. We can't do everything, so we won't do everything. So the real numbers are handy, and so anything to do with calculus really fits upon you're looking at things of real numbers. If you're dealing with computers only have a finite amount of memory. It's all about zeros and ones at the end of the day. So most things in computers can be converted to an integer, if you really think about it. So the internal representation of this whole computer that's using it really can be summarised by one integer if you really want to push it that far. So really what we're doing with discrete maths is much more looking at the sets based on natural numbers at the end of the day. And so if you're doing the theory of computation, that sort of thing, so this is what Church did and Turing as well. Then they were trying to develop a theoretical framework of computers. They really were looking at natural numbers and just looking at functions of natural numbers as the key way of doing it. And you can see remnants of that in Python. We are using the lambda functions, for example. And there's some fancy, and some of the fancy machine you see in various stuff. So, just a bit more about infinite sets, though. So all these are examples of infinite sets. I want to talk about the size of them in some sense. And so, if you've got a finite set, you can count all the numbers in it quite easily. So finite sets are called countable, because you just count them. But I also want to talk about infinite sets, which you can also count. So we want to talk about infinitely countable sets. So an infinitely countable set is one where you can you can literally count them. So 1, 2, 3, 4, etc. Keep going up in infinitum immediately. So, and so what that means mathematically is that there is a one-to-one correspondence between the natural numbers and this set you're talking about. So the set of natural numbers is obviously countable, because you can just list them all off. The set of integers and the set of rational numbers are also countably infinite. That's not obvious. I would like to try to explain it by using a little metaphor, though. So this is called Hilbert's Grand Hotel, Hilbert's Infinite Hotel. So let me give you this story. So Hilbert was a mathematician about 100 years ago. This is his little image to try to help you understand that infinity is different. Infinity is different. That was what his purpose was. So we have a hotel. The hotel has lots of rooms, an infinite number of rooms. They're all got numbers on them, so door 1, 2, 3, etc. So just numbered rooms, 1 up to infinity. The hotel's full, completely full. Every single room's got a person in it.
Rubbish. Well, then the world's overpopulated. We need to exterminate some people.
Okay, so there is lots of issues you can think about it. Imagine the waste it produces.
It's infinite waste.
But we'll ignore all that. Someone comes to the reception and say, "Can I stay the night, please?" And the receptionist says,
I don't know, man.
"Sure, no worries."
Check in the basement.
And so every room's full already. Every single room's full. She said, "No worries. I'll tell you what." So she gets out the in the column. So it's everyone in the room said, "Okay, everybody, you're now moving a room. So what I want you to do is I want you to pack your stuff up and just move to the room next to you, just one up from you are. So if you're room 2, room to move 3. If you're room 1,000,000, you move to room 1,000,001. Okay, so everyone does that. So everyone, and the process everyone's doing it said, "Okay, yep, you're fine. You just go to room 1 now." Sweet. And so therefore everybody's got a room, and this new person's being accommodated quite happily.
But they're not.
They are.
Because there's infinite rooms to be infinitely moving. The first room would never be vacated.
But everyone's moving at the same time, so you could do it in a...
But there's an infinite amount of people moving.
That's correct.
Doesn't mean it takes an infinite amount of time.
Yes, it would.
No, it all happens in synchronization.
That's ridiculous.
Okay, so
You're gonna hotel with infinite rooms.
we live in a finite world, and so you have to stretch your mind a little bit to accept it.
Ridiculous.
Now, in a finite hotel, that does not work. Why does that not work with a finite hotel?
Well, not everyone has the same level luggage, you
That's
see.
how infinite works.
So say you had a hotel with only 10 rooms, they're all full. Someone came along and said, "Can I get?" "Oh, sure." Everyone just move on one room on.
Yeah, the last one gets kicked out.
The last one gets kicked out. With infinite, there is no last room. So there is no last room for infinite hotel. That's the difference.
So infinity plus one.
Yeah, you'd be moving.
Correct. So did you hear that?
That would keep moving. I would move.
And you just be quiet in the background there. So infinity plus 1 equals infinity is sort of a conclusion we can draw from this. Okay, let's just push it a bit further. Suppose a bus comes along, and in the bus is infinitely big.
Not again.
And those people want to go to the hotel as well?
Yep. So again, there's seat numbers. So the seat numbers of the bus is 1, 2, all the way up to infinity. And the bus driver comes in and says, "I've got a lot of people in my bus. Can we fit them in, please?" And the receptionist says,
Yeah.
"Yes." How can they fit them in? The answer is yes. They can definitely fit them in. Absolutely. How can they do it?
Just move from infinity to the next room. Just do it.
Okay, the problem with that approach is that would take forever to do so.
This is maths. People buy 48 watermelons and no one cares why. Just
They'd rather do it either way.
So you have to do it that way. That's normal.
Just two infinities.
30 plus 1.
Technically, it has to be 2.
2 bracket infinity. Done. Done.
Okay.
Wow, you're a genius.
Thanks, man. That's
Oh, here we go.
I like we're going to leave the room.
I'm just sitting down.
Oh, they're going to stand up.
It's worthwhile thinking about. So where this corresponds to in maths, before I'll get you to keep not till you announce it yet. If you imagine all the numbers on the people on the bus, give them put a negative sign out of them, so they're all the negative integers. The people who are already in the hotel, we'll call them positive integers. So if you can squeeze them all in, essentially what we're proving is that the set of the positive and negative integers together have the same size as just the positive integers.
Damn.
Which is another way of saying, and in terms of what language before, that would therefore prove that the set of all integers is countable. Or countable infinite. So how do we do it though? How do you manage to squeeze every single person into that hotel?
With maths.
Okay, the answer is you need to get some space. So you get your receptionist gets the intercom. I'll give you the first half. Get the intercom. Okay, everybody. I want you to look at your room number, double it, and move to that room. So if you're in room 10, you'll move to room 20. Room 20, you move to room 40.
2 bracket infinity.
So everybody moves at the same time, which is why you can't shift. That's why you can't add on infinity. You can't just shift them sideways. You have to get everybody to move at the same time. What benefit does that produce?
You double the amount of rooms that you now have in an infinite scale.
You maybe. I want to make sure you can understand what that produces. You haven't done that with what you're saying yet. But what happens? What's room number 1 now?
Nothing.
2.
Nothing. Room 1's empty. What's happened in room 2?
It has the person from room 1.
Yeah. What about room 3?
Has nothing.
Every second.
Every even room has someone in, and every odd room has
Okay.
someone.
So by doing that little procedure, you manage to create lots of space very quickly. What do you do with that extra space?
Fill it.
Fill it.
Get
2 bus worth of people.
Another bus. 2 infinity buses.
No, I'll do more in a second. But essentially that's what you do.
Oh, God.
And that is basically you get all the people on the bus to fit on all the odd rooms. So you get your seat number for your bus, multiply it by 2, minus 1, that'll be your room number. You can squeeze everybody in quite happily.
Quite happily.
What if they can't do math to do that?
Okay.
There'd be some guy who never gets to his room. You're walking
There's
forever.
infinity.
Okay.
What if they've got Willy Wonka elevators that go sideways too?
So let's make it.
They go forever.
So let's make it a bit harder. So let's suppose that an infinite number of buses arrive. Each of these buses have an infinite number of people on them, and they all come. And the reception and the bus driver, the leader of the group comes in, and we've got a lot of people outside. Can you fit them all in, please? And the answer is yes.
This reception's going to get big.
The answer is you can actually do it. It seems a bit unbelievable. You've got an infinite number of buses, an infinite number of people, lots coming in, but you can squeeze them in. Let's make it slightly easier by just assuming the hotel's empty, or it doesn't really matter. You can fit them in anyhow. How you do this is essentially everyone has a bus number and a seat number. You add those 2 numbers up. First of all, you look at all the people whose sum adds up to 2. How many of those people that would be?
2.
So how many people have a bus number plus seat number equals 2?
2.
And they are?
1 and 1.
Yeah, so there's only one person. He's on bus number 1, seat number 1. It's just the one person. He gets to go in first.
Lucky.
Then everybody whose seat number plus bus number is equal to 3 gets to go in next. How many of those people are there?
1.
Two of them. So but bus number 1, seat 2.
But seat 1.
And bus number 2, seat 1 would be the next 2 people.
Yeah.
You do, and the order they get to go in will be based on their bus. So the guy from bus number 1 gets to go in first.
Yep.
And you keep going. So for the next lot, everybody whose seat number plus bus number is equal to 4 would go in next in the order of their buses.
Is that 3?
And if you thought hard enough about it, you could tell any single person what their new room number is. I won't go for the formula because you'll spend more time than you understand from it. But you could do it. I guess that's the point. Is that...
Would you though? It's really the moral thing that I would...
Well, why do I... What's the purpose of this example? Why am I mentioning it? If you imagine everybody's bus number is the top of a fraction, everybody's seat number is the bottom of the fraction, then every single person coming in really can be represented as by being a rational number. So what this is essentially showing you is the set of all rational numbers is the same size as this hotel, which is just the natural numbers. So it shows you that the set of rational numbers is countably infinite. That's the implication of it mathematically. Now you can go further. You can make each bus have an infinite number of decks, and it all still works out.
Oh man, let's do that.
And then Donald Trump gets on a bus and ruins the whole...
and you can...
Build an infinite wall around the nuclear.
So, as long as there are a finite number of infinite dimensions, it's fine. If you go to an infinite number of infinite dimensions, then it breaks it.
There's an infinite number of...
And how would you ever do that? And that's a set of real numbers. So this is important to mention. The set of reals is not countable. So if you had some train coming in, and everybody's number was given by a real number, then you could not fit them in this infinitely hotel. It's not big enough to fit all those in. So the set of real numbers is in some sense bigger than the set of integers. Because you never. So it's and the guy who proved that. So Candle's diagonal argument is a good way of proving it. I won't.
Did he go insane?
Why do people believe this guy?
Because he's like, what if you had...
No, it's a real...
Everyone's like...
I can take you 5 minutes, but I think I'll probably best do other things. So I'll ask if you want to. Tell me in the lecture. I can tell you 5 minutes what the proof is. It's not complicated. It's actually really nice.
Okay.
Because the simplicity of it all. But so you can do all these things. So I guess at the end of the story, what do I want you to remember? I want you to know what a finite set means. What does finite mean?
It has a limit.
Has a limit. A countably infinite.
It's a real. No.
So countably infinite means set of integers, set of rationals, or things like that. Any subsets of those will be countably infinite. Things you can just count. So any subset of integers, like the set of all even numbers, the set of all numbers divisible by 3, all those will be countably infinite because you can count them. The other one is infinitely uncountable, and that's pretty much any real sets or intervals. So bunches of real numbers, essentially. So the set of all real numbers between 1 and 2 will be uncountable.
Man, this is too many. There's infinite. Oh god.
So Cantor, which the guy developed, is realised that there's not... Infinity is just too vague a word. You're not talking about different orders of infinity.
God.
So the set of reals is more infinite than integers. But we won't go any further than that.
The university's too much for me.
Now, if you're getting worried, all that's what I want to know. If you go look at your assignment 1, all I want you to do is just those simple definitions. Be able to tell the 3 apart. That's all I'm looking for. Just to be able to tell those 3 apart.
That's assignment 1.
One of the questions on assignment 1. So, it's good to... So, infinity does stretch your mind, and I encourage you to actually do that. I think that's a useful thing. But that's the sort of things I'm looking for. Okay. So some other definitions, and why I want to talk about this is because it's useful notation, various stuff. That's the idea of a power set. So a power set is the... So moving on from infinity, so this is just back to finite stuff now, makes it a bit easier. We can visualise it. The power set is a set of all subsets. let's just make one up. I'll make it. Okay, this is our set A. The power set of A is the set of all subsets of it. So tell me what sets are subsets of this one here. Can you tell me some of them? Yep. Thank you. That's the one baseball forgets. So I've got it already. Excellent. So the empty set is a subset of it. So that's good. What else do we have? So the set containing 1.
Set containing 2.
Yep. Anything else?
Set containing 1 and 2.
Yep.
I was totally guessing that.
Anything else?
You got it. You can guess, right?
Can you flip the 2 and the 1?
2 and 1 is the same thing. So because the order doesn't matter, right? So that's the same as 2 and 1. So we don't need to write it down the second time.
Could you do like the empty set and 1 and the empty set and 2?
If you try to join the empty set onto anything else, empty set doesn't provide any elements, so it would just produce 2 of those. So that's the answer. So I'll write that off. So that's it. So the power set of this one is just those 4 different sets.
Cool.
And the last one, as a few people remark, is the same as saying 2-1. That is actually the same set. So it's just a set of all sets that are contained in A.
What about like 5, 5? Like 5, 5, would that?
We don't know how to combine sets just yet, and so you can't just put 2 sets next to each other. You have to do something with them. So when we put 2 integers next to each other, we mean multiplication. We have an applied operation of them. We don't really have that for sets at this point in time. So I want you to pull out a piece of paper. I want you to write down what is the power set of B. What's the set of all sets which are contained in B?
The set of sets.
So the set of sets, yep. So it's going to look like that first one. It's going to have a few more in it, that's all.
What about like the set of 5, 5? Would that fit in A?
So that would not be contained in A.
It's just 2 nothings.
Because that's a set containing 2 elements, neither of which are in A. So.
And nothing's in.
So
It's a bus. Just put a bus there.
An infinite.
An infinite bus.
okay, so this is a mean example. I'll be honest with you. I fully expect you to be able to get it. What the difficulty here is that we're starting to mix the idea of what an element is and what a set is. That's what's getting difficult. So normally they're quite distinct. You go, I've got a bunch of elements. The set contains elements. Nice and happy. Where it gets difficult, where this is starting to touch on this point in time, is where I'm talking about sets as being elements of other things, and that really can be hard to grasp. So let's do it. This is a nicer example where that happens. It is a nicer example. So let's get it here. We'll go for this one. So have to let it go. It's good to have a go at yourself and yell out some answers. If you get them wrong, only you'll know, and that's okay. And I do like Magic School Bus, if you've ever heard of that as well.
You mean the TV show or something?
Yeah, the TV show. And why is because Mrs. Frizzle, or whatever her name is, says making mistakes is okay. She's going, have a mess, make mistakes. That's the idea. Making mistakes is good, it helps you learn. So don't be afraid to make them. Anyone tell me what they reckon some of these subsets are?
We've got 5.
5, yep.
And just 1.
Set of 1.
Just 2.
2,
Just 3.
3.
1/2.
So there's
Instead of 1, 2.
1 and 2.
1 and 3.
2 and 3.
1, 3.
2 and 3.
2 and 3.
And 1, 2 and 3.
How do people go?
Yeah.
They want to.
I did it on the spot. 10 marks.
Oh, I was saying, seriously.
Empty set. It's called phi. It's the
Pretty much just right out. The other one is a couple of strings.
it's the Greek letter, and that's how you write. In English, it's PHI. That's how you write that in an English word. So empty set. That's how I normally write it down as. So that's how many. What's the size of that? How many elements are in that? What's the cardinality of that set? Okay, what? So, what's the size of this set? What's the size of this one over here?
Why are people saying 8? Or are they saying 8?
8. I would hope. I hope the 8 is size would be 8.
So people actually. So why is it 8?
1, 2, 3, 4, 5, 6, 7, 8.
Oh, I thought you meant. Okay, cool. I thought the arrow was pointing to that set of 3.
Okay.
I was like,
2 to the number of elements.
yeah.
What's the size of the power set? That's what you're saying. Explain it, and I'll try to write the symbol down for you.
2 to the power of the number of elements in the original.
Yep. So the general pattern, which is what you just said, is that one there. That's how you. So the size of the power set is to the power of the size of the original set. It's correct, absolutely.
So it's like kind of like an arithmetic equation.
The reason is it's actually fairly simple. In each set, either you have to pick an element or you don't. So every time you've got 2 choices, in or out. So for every element in the original set, you either got 2 choices, and you multiply that. So for this one here, for the PB, you had 3 elements. Each is either in or out, so you've got 2 times by 2 times by 2. That's where the 2 to the power of comes from. But it's good to see John Patch, so well done. Okay, so this is just getting you to think about what all the notation means. What's that one? Can you say that in words? What that one says? What is?
Power set of phi.
What is the power set of phi?
That's not phi though, isn't it?
Hmm?
Or is that phi? So everything is a slash.
Yeah.
Cool.
Which is an empty set. So the power of an empty set.
Right.
Which is 2
One.
So it should be 1. Yeah.
Okay, so it should have one element in it. What's the one element it should contain in it then?
Phi.
Phi. That's right. That's the one element it contains. Okay, so these are some nastier ones, and why I do this is some are straightforward, some are nastier. The nastier ones takes a bit while to understand, so I want to give a chance to explain them to help you understand it. Okay, so we've got a set which just contains 2 elements, it's A and little a, little b. I can make them 1 and 2 if you wanted to, doesn't really make much difference. So I want to work out which of these statements are true or false. So we'll just go show of hands. So the first one, is the set A contained in its power set?
Yep.
Yes, that's right. So A is a subset of itself, that's what it pretty much says. So yes, that's fine. What about the second one?
Well, yeah, true, because...
Oh, I said it. Wrong thing, didn't I? I said the wrong thing, so I should... So A here is, let's make it 1 and 2, make it a little easier. What's the power set? We said it before. Phi 1, 2, and 1, 2. So the first question is A a subset of PA? So is this thing here containing the set? And he says yes. is A contain an A? Is A a subset of itself?
Yeah.
Yeah. What else we got?
Like a whole weekend. That should be fun.
Where's the one? Is A an element of P of A?
Yes.
You're going, there is right there, yep. Oh no, so this is right. I knew I did something wrong. That's wrong. That's no. That's why I went back over here, because I realised I made a mistake. So everybody makes mistakes. It's okay, as I said before. I have to figure it up though. So why is the first one false? Or did I get tricked by it? Why is A not a subset of its power set? Subset means every element of the first one must be contained in the second one. So every element, so 1 and 2, there's only 2 of them, have to be contained in the second set. Is 1 in the power set? No, because the power set only contains sets. So it doesn't work, it doesn't fail straight away. So this is where it gets tricky, and you can see how I get tricked up on it occasionally, is that we've got to talk about different things. So it's false because A is a bunch of elements, power set's a bunch of sets, so elements aren't contained in the aren't sets. That's pretty much why it's false. Next one here is the set of A. The set containing A, is that inside of P of A? So if you write it down in symbols, that'll be the set containing 1, 2. Is that particular set, it's a set, is that contained in the power set?
Yes.
No, actually, because there's double braces.
Trolled.
So A is in P of A, that's right, but not the set of A.
Right.
Because you're putting 2 lots of brackets, double braces, 2 lots of curly brackets there. You've got a set of a set, and you go, it's too much. What in the last one? The next one though, that's false. So is the set containing A, is that a subset of P of A?
No.
Yes.
Maybe.
So I'm getting one person saying the answers. I want more people to think about it. You can know the answers before I say. So what does it mean to be a subset? So if this is true, that would tell you that the set A. So this is the equivalent way of saying that A must be in P of A. So it's the same thing. So those two are equivalent. So to say a set is one set's a subset of another means every single element in that one must be an element of the other one.
Sure.
So that's what they'll be equivalent. Is A inside of P of A?
Yeah.
Yeah, there it is right there. So that one is actually true. So is the set containing A, is that a subset of the power set? And the answer is, well, yeah, because every element in it, A, there's only one element in it, that is contained in the power set. Okay, so that's one of the one possible set. That's like one possible subset of A. What about the next one? So in terms of the language I've put, that was 1. So it's a set containing 1. Is that contained in the power set?
No.
Yes.
Yeah, so just reading it off. So that one is actually, I can see it there. So the next one is the set of A subset of P of A?
No.
Why not?
I don't know, because the one above it's a yes.
Okay. I like that. I like that way of thinking. That's good. That's good. Using
It's worked.
it's correct. It's correct.
Like the first one was correct, and the second one was wrong.
So why? So if this was true, that would tell you that every element inside that set, so just A, would be contained in P of A. So these two mean the same thing. So if something took a subset of something else, every element must be in the other set. So is little a, or in this case, well, it's 1, isn't it? Change the numbers. Or is the number 1 contained in the power set? Well, the power set's just a bunch of sets. It doesn't contain numbers, it just contains sets. So that's why it's not true. I mean, you used lateral thinking. I like that. That's also good. Okay. 3 more and then we'll finish off there today. Is A inside the power set? No, we just said no already. Is the set containing A in A?
No.
Why not?
A's power
Because A's got A is just 1 and 2. A is a bunch of elements. You can't have a set inside it. The last one.
Yeah.
So the last one is the set containing a subset of A.
Yeah.
That's just a quick way of saying, is A in A? Quick way of saying, every single element has to be inside of it.
Yeah.
Yeah.
And the answer is yes. Okay.
That's pretty straightforward.
So some of those were difficult, let's be honest with ourselves.
Understand?
So what I want you to do is I want you to go back to the study guide, which explains these things again. You can read that if you want to or not. I don't really mind. It has some exercises in there. I want you to try those exercises out for practice, just to cement some of these things in. So the things I really wanted you to take away is a sense of it's a collection of things. Order doesn't matter. Can be anything you want to at all. So I think most people get that one. I want to talk about 2 key ideas. The idea of being in it or not, that's the in, and it being a subset or not, subset idea. So you're going to talk about it later. It's usually have a few key examples, such as natural numbers and integers and stuff work. And so they're just some reference examples to handy. But I want to get a handle around those things. There are useful tools to help describe them. Venn diagrams, we'll get onto those tomorrow. So they are going to be more useful and practical skills about how to do with it. We're just trying to get an idea of what does this all mean. And before, I'm not trying to scare you off. So in order to do so, I should tell you the caveat. Most of the time we aren't so highbrow as this. So this is just happens where it starts with. So we do other practical exercises as well. So don't run away or anything. Or not yet. You can. So I'll see you in lectures tomorrow morning.
Yay! Research.